So now we'll take a look at an example of surface area calculation done in polar coordinates. So this kind of thing happens fairly often because you often have surfaces or functions that are radially symmetric. So here we're going to look for the surface area of the part of this surface here, x squared plus y squared plus z equals 1, which you may recognize as a paraboloid. And we're going to take the part of it that lies above the plane z equals minus 3. So let's see. So first off, we're going to be considering z to be a function of x and y. So we'll solve this guy for z by subtracting over the x squared plus y squared to the other side. And notice this part that I've got here in parentheses, I did that to highlight the fact that this is 1 minus r squared in polar coordinates, right? So that's why we're going to use polar coordinates for this example. If I graph this function, so here's the f-axis and here's my good old x and y, it's going to look like some downward opening paraboloid like this. And I guess down here, so somewhere down here is where we have the plane z equals minus 3. Slicing it, it passes through the xy plane up here, just to ground it a little bit. And let's see, so we need to figure out what our bounds are for this integral. So in particular, I want to know what the region is right here that we're going to be integrating over. So what is this domain? That's going to come from the intersection of, on the one hand, z equals minus 3, and on the other hand, 1 minus x squared minus y squared, which, if I put this part back on the left and this part back on the right, is going to be x squared plus y squared equals 4, or the circle r equals 2. All right, so converting everything to polar form to set this guy up, we have f of r theta is going to be 1 minus r squared, as noted before. And so for our domain in purple here, I guess I should emphasize this is the part we call D. We've got r is going to be going from 0 to 2, and theta is going to be going from 0 to 2 pi because we have a full revolution. And our dr, and this is why I hate that this book calls this r, because this r has nothing to do with the r inside the square root, which is our independent variable for radius. And then we have our area element, which in this case is going to be r dr d theta, and that dr is not the same as this dr. Here, I'll make it boldface so it looks a little bit different, but come on, people, choose a different letter, for the love of God. Okay, and rant. The area then of this this surface, this graph of f, is going to be, yeah, do we want to call it S? Do we want to call it graph of f? Let's call it both. Same thing. Okay, so this is going to be then, and now I'm going to set up the integral over this region. So we're going 0 to 2 pi for our theta, and we're going 0 to 2 for our r, and then we have square root of 1 plus 4 r squared inside, and then we have our area element r dr d theta, and now we just remains to crank this sucker out. So let's see, so good old u substitution comes in handy once again. So our du is going to be 8r dr, And I guess I will divide that over to the other side there. So I've got my RGR right here. That'll become 1/8 du. And for this one, we're integrating over a rectangle in the r theta plane, right? So this is a rectangle in the r theta plane. So we can pull this out as integral 0 to 2 pi d theta times, and then we've got the integral from 0 to 2, 1 plus 4r squared inside the root times 1/8 du. Oh, whoops, I forgot to switch my guy here. Okay, so there's my u to the 1/2 now. Sorry about that. And okay, so the first part becomes 2 pi. Then the second part becomes u to the 3/2 times 2/3, and we've got a 1/8. So we've got some cancellations going on here. 0 to and now we've changed the bounds, right? I forgot to change the bounds. So as r is equal to 0, u is going to be 1. And then when r is equal to 2, we have 2 squared is 4 times 4 is 16, so 17. All right. Okay, so now let's see. So now we've got some cancellation action between these 2's and this 8, leaving behind a 2 on the bottom. And so we get a pi over 6 out front. And then we have the quantity 17 root 17 minus 1 root 1, aka 1. And there is our lovely little answer.